So we got some homework that's coming up, so why don't we have a look at that? And also I just want to make a couple comments about some of the homework that I've been turning back. I've been turning back the paper homework for students that turn it in that way, because I can get the Moodle stuff back with a little bit more flexibility, so I do get the paper homework back first, just while people are here. I need to do that. I'll get to the Moodle stuff, but I've got one more thing to do, then I'll start getting on that. All right, so a couple of things here just regarding some of these things. First thing is that our midterm 2 will be Thursday, okay? And that'll be next week, of course, and that will be the 27th, okay? All right, now this one here I turned back. Now, here's the thinking on this. If you want to find the stress on AB, here's how this goes. What you have here is the shear. You'll notice the shear acts, the torsion acts down. What that will do will cause a downward shear on that plane. So what we have then, if we look at a differential element, is a downward shear like that. And I can't remember what that number was on that, but you would calculate that. It's torsion times radius divided by moment of inertia is how you would figure that out. All right, that's 281. It's 1.89 megapascals. All right? So you start with that. Now, the other shear meets in the corner, and then, of course, the other two meet in the opposite corner. So that's what the biaxial element looks like there. And it comes from the direction of the shear on the end of the shaft. So any questions on that? So what that means is that tau xy is equal to negative 1.89 megapascals, because that shear is down on the reference plane. This shear would cause the element to rotate clockwise, so it's negative. So when you put that into any formulas, it goes in as negative 1.89, okay? Now so we good with that? Okay. Now the other thing is this angle here is not 28, it's 28 plus 90, it's 118 degrees. Okay? Because when you're doing stress, which you were asked to do, the angle is from the vertical plane. So that would be 118 degrees. So now if you want to start finding the stress on that plane, those are the inputs right there. So you do need to be conscientious about this stuff. It can, now sometimes, and actually it's not uncommon for it to kind of come out in the wash, so to speak. So sometimes the signs kind of take care of themselves, or they balance out in some way. But you do have to be careful about this, and it's important to put the stuff in properly. Okay, so if you're going to find the normal stress on that plane, so that would be for torsion, what sigma x1 is tau xy sine 2 theta. That's equation 97. Okay? If you're going to find the stress on AB, the way you do that is that's negative 1.89 times the sine of 236. Okay? That's the proper way to put that in there. Okay? And a lot of you didn't have that in there. You didn't have the right inputs in it. I didn't really take any points off because, I didn't want to go through and do all that. It wasn't that big of a deal, but it is kind of a big deal. You put the inputs in properly. So I want to call that out, that's how you should have calculated that. Yeah?
So when do we use the horizontal plane?
The horizontal plane is for strain, but the vertical plane is for stress. And by far, I think the most common thing you look at for this biaxial stuff is stress, really. I mean, that's far more common to look at that than it is for strain. but the vertical plane is the reference angle for strain. Okay. Similarly, if you want to find tau x1, y1 for AB, again, that would be negative 1.89 megapascals. And that would be times, I think it's cosine of 2 theta, so cosine 236, okay? And I ran out of room there, but tau xy, x1, y1 is tau xy times cosine of 2 theta. Okay, that's where that formula is coming. And that's only for torsion. And the reason that you use these shortened biaxial formulas is for torsion. Sigma x is 0 and sigma y is 0. There isn't any stretch or compression on the xy planes with torsion. It's all shear. That's what you're looking at. Okay. So we got questions on that? Yes.
Can you explain why this year the negative 1.89 is negative one more time?
Okay, what's happening here is you're taking the front or the far right side of that shaft and you're twisting it such that you're twisting it down across the front like that. So what that does is it exerts a twist on the element the same way, like that. And that translates into a shear that acts down on that face of the element.
So if that torsion was going the other way, we'd still have negative shear.
No, you wouldn't. If the torsion were going this way, it would be positive. Because what would happen on your element then, I'm starting to run out of room, but it would go that way. See, that would be positive shear. So the direction of the applied twist creates the shear on the element, and that's how you find the sun. Yeah.
So if the torsion was at the back somehow of that shaft, would it translate to the other side of that vector? Does that make sense? So like if it wasn't attached to the wall, and there was a torsion moment at that point.
If it was in balance,
right,
they would be equal and opposite. Oh. As long as it's not accelerating. So the shear here would be reactive. It would be doing that, going up across the face, which, like that. There. So that's what causes this to go up. Okay. Good.
So is it safe to do the opposite of the right-hand rule?
Yeah, unfortunately. Yeah, you're right. It's the opposite of the right-hand rule. You're right, because that's actually a positive applied torsion, but it creates a negative shear. They don't align.
So it'll just be opposite.
Yeah, it will. Right. Okay. Okay. So yeah, the torsion space in the right-hand rule, that on this example, it is positive applied torsion, because by the right-hand rule, your thumb would point that direction, and that would be positive. But it creates a negative shear in this case. Okay. All right. We're good with that? I just want to point that out. And these kind of details, just pay attention to them. They matter, okay? Keep in mind that when you're doing stress and biaxial, you always measure from the vertical plane. That's just the convention. It's not some, thing that should make intuitive sense either. It's just how somebody set it up 150 years ago when they generated the equations. That's all it is, really. Okay? So, just remember it. It's just something you got to remember. Okay? All right. Now we got a few of them coming due here tomorrow, so let's look at those. So 311, this is kind of, the more basic kind of classic approach to these. The next one after it is also statically indeterminate, which this one is, but it's a little bit more involved, the next one. So, let's kind of deal with that. So what we're going to, now, here's kind of what I think about when I do this is if I take that position on the shaft and roll it up, there's going to be torsions coming back the other way. These are reactive torsions, so sometimes I put an R on them, TRA and TRC, like that. And the fundamental statics relationship is quite simple here. It's just that TRA plus TRC is equal to what's applied, 80 pound-feet. Okay. Now, I'd probably get that 80 pound-feet and make it into pound-inches. That would be 960 pound-inches. All right. Now that's the statics part. Now that isn't enough to solve it though, because you got one equation, you got two unknowns. So the other thing you look at to solve it is look at the angle. So the angle from A to B is equal to the angle from C to B. They're both the same angle. See, they're the angle at B is what they are. You can calculate them from both directions. So that's the thing. And what phi equals is TL over IG. Okay? So that's the second equation. So that's basically how you solve these things. You use both relationships. So this allows you to go a bit beyond statics. This is the thing. All right. So the unknown is T. You know, you've got the length. You can find I. It's just a solid shaft. You know, it's easy enough. It's 0.03, 106 inches to the 4. And then you've got the modulus. For the aluminum, it's 3.8 times 10 to the 6 pounds per inch squared, okay? And then you just set that equal to the information for the steel. And then you can work that down and you can end up with a relationship either between the aluminum and the steel, or the steel and the aluminum, you know, however you want to do it. So the torsion from A to B is equal to 0.6 basically, times the torsion from C to B. You can also invert that, you know, however you want to do it. The torsion from C to B is equal to 1.67 times the torsion from A to B. You can work that either way, okay? So now you've got two equations and two unknowns, and you can solve. That's basically how this stuff works, okay? So that's what we were going over yesterday a little bit, and that's the deal here. So we got questions on that? The unknown is there and there. Okay, so this would be the torsion from A to B, which is the torsion in the aluminum. Okay. So what you know is the sum of those two torsions is 360, or excuse me, 960. And then you know the ratio between them. So now you can go ahead and do just basically the two equations and two unknowns and solve it out. What you're going to end up with when you do that is you'll get the two torsions. The torsion at A, which is really the torsion from A to B. And that's going to be 360 pound-inches. And then the torsion at C, which is the same thing as I'm calling the torsion from C to B, is 600 pound-inches. And then you've got the angle is TL over IG. And that is 0.0914 radians equals 5.23 degrees. Okay. Questions on that? Okay. So that's kind of a bit more basic style of this statically indeterminate stuff. Okay. Like that. Now we got a little bit trickier one next. Okay. So do we have any questions on this? And you want to find the moment of inertia. Like so. Okay. All right, now what's happening here is we want to find how much of a load can be applied to those armatures. So what you would do with this one is have a look at basically the couple that's caused by the armatures. Okay, that's basically how I would do that. So I would have what I would say here is I've got the reactive torsions here. Torsion at A and the torsion at C. Okay. Like that. And so the statics here, what you would do is you would look at the armature, and I would do it from the side. And what you're going to have here, or excuse me, as you're looking down the shaft. So what I'm doing, I'm looking down that way. And what I'm going to see are these loads P and P. You know, if you remember from statics, you deal with a couple. Well, that's what a couple is, okay? It's the force and their offset distance. So we got 0.375 and 0.375 and 0.75. So I think that's going to be something on the order of about 1.5 inches. Okay. Now, if you look at a couple, the torsion then that's applied will be the offset distance times the load, it's FD. And that comes from the fact that you've got half of the offset here on that side and half of the offset down. So you got half of the offset on either side. When you add the two together, you get to just get the offset times the load. So you get 0.75p plus 0.75p. They're actually negative as I have it drawn there, but let's not worry about the signs, so much. It's just the magnitude of that is 1.5 times p. So you good with that? Okay. So that's how you can find the load, is use that expression there for the torsion. So what you're going to do here for statics is you're going to add the two reactive torsions together, and they're going to equal the 1.5p. So you're going to get TA plus TC is equal to 1.5 times whatever p is. So we could start with that. All right. All right, now that's the first bit. Now, we obviously got a lot of variables there, and too many to handle, with just that simple equation. We got more going on than that. So we'll have to do the rest of this. All right. Could you tell me, I've changed this problem around over the years. What's your dimension over here? Is it 18 or 15 over there? Okay. 15? Okay, thanks. That's what I thought, but I wasn't sure. So that should be 15 inches. Okay. So there we go. All right, so now the next thing to do is to look at a couple different things here. The next thing I would do is I would say that TA times LAB over I sub P for AB over GAB, that's going to equal torsion at C times LBC, or actually maybe more properly CB, over I sub P CB and GCB, okay? And I'm setting that up because that gets me the angle at B, okay? Like so. Now you can work through that, and what you can end up with when you do is you can get the ratio between the two. So you can get that the torsion at C is equal to 0.778 times the torsion at A. It's like trying to write on a postage stamp sometimes with this computer, but It's all good. I just kind of bump things with my hands sometimes and they just scroll it around. So 1.285 times T sub C. There we go. So we'll solve it either way. All right. Now, the next thing here that you've got is you've got some criteria on this, and the criteria is you've got a maximum allowable shear stress. It's 60,000 psi. So tau max is 60,000 pounds per inch squared. Okay. So what you want to do is relate that to the torsion, because the shear is this whole other variable to throw in. You know, we're getting so many variables here, we can't handle them all. So we're going to have to get that shear translated into a torsion. So the way to do that is look at what the shear is. It's TR over I. So if you want to find the torsion, you go the shear times I over the radius, okay? And this will be the maximum torsion, okay? And really this formula here is for tau max, is what it is. So if I want to find the maximum torsion, what I'm going to do is I'm going to take tau times I sub p divided by r. Okay, so now I can go ahead and find the maximum torsion at A by applying that formula. And what that's going to get me is 3989 pound inches. And then I can look at the maximum torsion on the other side, which is at C, applying that formula, and I'm going to get 4970. Okay. So we good with that? Now, these are independent of each other. They're not tied together directly. They're not going to occur at the same time. So whenever I'm looking at this kind of problem, I think about putting a wrench on here and just turning the wrench, you know, like that. And just keep turning it and turning it and turning it until the stress hits 60,000 psi. So if I take the A side out to its maximum of 3989, let's see what C would be. So if the torsion at A equals 3989, the torsion at C will be 0.778 times that. And that'll get me the torsion at C. And if that's the case, the torsion at C is 3103. Now, 3103 is less than 4970. So that's okay, all right? I can push A all the way out to 3989. And if I do that, C will still be within the limits. It'll still be less than the 4970. And if the torsion at C is less than the 3970, that means the shear at C is less than the 60,000. It's kind of the chain there, okay? So we all right with that? So what I did there, I just found, based on the allowable shear, what the torsions can be on either side. Then I said, okay, if A goes to its maximum, what's C going to be? C will be acceptable if A goes to its maximum. Now check the other side. Now I think it's going to be okay, but all the same check. If TC equals 4970, what will TA equal? And is that acceptable? Now I don't think it's going to be, but all the same, check it, okay? Make sure, figure out what we're doing here. We're figuring out which side maxes out first. So if I just put a wrench on that and start turning it, TA is going to hit 3989, and I think at that point I got to stop because TC is still okay. But all the same, check, just for your own, just to kind of understand this process a little bit, check if you take TC out to 4970, what's TA going to be? And I'm pretty sure it's going to be too high, okay? But check it anyway. All right? Y'all okay with that? All right, so now what you know is that TA plus TC are equal to 1.5 P. So you can plug in the acceptable TA and TC. Well, first I obviously can't spell acceptable, so that's a problem. But let's see. So we're going to plug in the actual values, let's say, for TA and TC. Such that neither causes tau max to exceed 60,000 psi. Okay. And I think when you do that, you're going to end up with 7,092 is equal to 1.5 times P, and that will get you P. And P will be 4728 pounds. Does that make sense? So there's an extra check in there. You got to you have to determine, which one of these is going to max out first. You can't push both of them to their maximums. The idea is that 3989 and 4970 do not occur at the same time. If you put a wrench on that and start twisting that, you're going to hit one or the other first. And when you hit that, you got to see what the other one is corresponding at the same time. Add those two together, and that's what the applied torsion equals. Okay? So there's a little extra process in there. Plus you have the bit with the couple in there too, that the torsion is 1.5 times whatever the load P is. Okay. So we good with that? Okay. All right, then the last one here is this finding the torsion in the shaft. Okay, and then we want to size the shaft. So the first thing to do was to find the torsion, and we want to get to 32,000 pound-inches. And what that equals, when you find that, is that should be force times distance. Okay, now the force is right there. That's the force, and here's the distance. We're assuming that force coming from that plunger is perpendicular to the plate that sticks out of there. And then we're going to take that force times the distance. And that should come out to be 32,000. Now, the thing here on this one is that to get that force, there's a common thing we're given that plunger pushes with 4,000 pounds. You don't take 4,000 times cosine 30. You take 4,000 over cosine 30 to get the force because of how that trigonometry works out. Okay. So are we good with that so far? We got any questions on that? And everyone was here, right? Everybody got a copy of this thing? I think everybody's here. All right. Now once we got that, now we have the torsion. All right. Now you know what the allowable shear is, okay? You know that the allowable shear that was given, and that's 5,000 psi. Now that equals, of course, the torsion times the radius divided by I, and you can then solve for R. because you know that I sub p is what, pi over 2 r to the 4, right? So you can solve for r using that relationship. Now the other relationship you got to look at on this thing is the angular one. And what you've got is phi is equal to TL over IG. Okay? Now, when you do this, you're going to solve for R again. So to solve for R, you have to know what the torsion is, which we found. You have to know the length, which we've got. You got to know G, which you've got. But you also have to know the angle. So you plug in a known angle into that formula, and based on that, you can find I sub p. So are we good with that? All right, so the allowable twist angle in the shaft is what that's going to be if you're looking down at the shaft. What's happening there is if you start with a horizontal line, if you're looking down the length of the shaft, that'll twist, okay? Because what's happening here, to get here, you've got I think it's 0.275 radians per second in 2 seconds, right? So the back of that shaft is going to turn. Now the front of the shaft has a different thing going on there, okay? The front of the shaft is based on that angle right here, okay? And I think we all figured out that the front of the shaft needs to turn 30 degrees, okay? So what's happening there is if the back of the shaft turns a certain amount, but the front of the shaft only has to turn 30 degrees, that means that the shaft itself can wrap a little bit, okay? Because the back of the shaft is turning more than 30 degrees if you look at it. It's more. So if the front only has to turn 30, you can have that shaft twist a little bit. Not a lot, but a little bit. And I think it's somewhere, the back twists somewhere between 31 and 32 degrees. I'm not sure what it is, and I actually looked at it in radians, so I don't know what that back number is, because I've got it in radians. But what you've got then is you're going to have a little slack there, a little bit of difference between the front angle and the back. And that's going to be your twist. Are there questions on that? Let's see here.
So specifically, we're looking at how much the shaft is binding up.
Yes, you might say that, yeah. And right, and it's kind of, if this backside goes, let's just to make it simple, 32 degrees, and the front side only has to go 30, you can have a little bit of twist in the shaft, because you can have a difference between the front and the back. That's basically it. And I'm just trying to illustrate what that twist is in a shaft. We good with that? Okay. So now, once you've got that, you know what phi is. You're going to solve that. You're going to solve that for r. Okay. And again, the moment of inertia is pi over 2 r4. So you should be able to solve twice for the radius. And then just pick the one that applies. Now, do you want the small radius or the big radius? Yeah, the big one, okay? So probably the simplest rule when you're designing stuff. If you get different sizes, pick the big one, okay? Because it's less likely to break. If you come up with different loads, pick the small one, okay? Because that's what you want for load. So, well, I guess that depends a little bit on how you look at the load part. But generally speaking, when you get sizes, if you got more than one size that you calculate, you pick the biggest. If you got more than one safe load that you're calculating, go with the smallest loop, is what you would do, okay? All right, and now once you have that, you can then find the shaft sizes. And pick the bigger one, double it, and then I want you to round it. And I think, what does your handout say? Does it say to the nearest eighth of an inch? Or does it say quarter? Okay, let's go to the nearest quarter, okay? It's just a little cleaner, okay? So round to the nearest quarter inch. Now, you're going to round down or up? Now, that's an obvious answer, but yeah, up, okay? Okay, that's run number 1, okay? Now, run number 2 through this is I want you to do one other thing, and that is tell me if instead of using a solid shaft, if you have a shaft that has a 4-inch diameter, what size hole can you have? Okay. Round it again to the nearest quarter inch. Because normally speaking, you're not custom fabricating your own shafts. You purchase them if you're building stuff, okay? So you round them to round numbers. Okay? So just use the same numbers that you had before and figure out what size hole to put in a 4-inch shaft for that. Okay? Now remember to round that. Think a little bit about the rounding on that one too, okay, how you would do it. Okay. So we good with that? We got any questions on this one? Yeah. So that's just a little bit of a design problem, okay? So a lot of times, you're presented with analysis equations. When you do design, sometimes you got to rearrange them and just solve them in a different direction, so to speak, to get sizes and things like that, strengths and sizes, things like that, okay? Okay, we're good? All right, now we do have that, so that stuff's due tomorrow. We do have the test coming up on next week on Thursday. I just handed out, and it's available online, a little bit of a test review. We got a couple minutes, so let's just have a look at that. All right, this is the stuff since we've done biaxial stress. So we've got Hooke's law, which goes 2D stress to strain and 2D strain to stress. Strain energy density and volume change I didn't cover, so they're out, okay? Plane strain we have. So we did do a fair amount of sketching, okay? There's 3 kinds of sketches you could make. Schematic, which is like problem 231, rectangular plates, which is like problem 221B, and then the circular sketches, which we did in class. So just be able to handle those sketches. A lot of the schematic is just to show the dimensions. The rectangular plate, a lot of this is kind of about reference points. The rectangular plate, that's the reference points. Circular works well when you've got a middle reference point. Okay. Okay, the biaxial strain, there's just equations for it. You should know how to calculate epsilon x1, gamma x1, y1, and alpha. You should know what those things are. Keep in mind the difference between these two things, okay? All right, we did hoop and axial stress on pressure vessels. We did stresses and strains in a pressure vessel. For shear, we did the shear and twist angle, the multiple torsions applied, the biaxial stress and strain, power transmission, and indeterminate torsion. So that's the topics for this one, okay? So basically we got Hooke's law, we got biaxial plane strain, we got pressure vessels and torsion. I've got a few problems here. First one I think is just pretty basic torsion definitions. The next one is kind of an indeterminate kind of problem there for torsion. Then I've got find the stress on this plane in a pressure tank. Remember to use the proper angle on that. And then I've got find the length of a line there after the strains are applied. So that's biaxial strain, plugging in the proper inputs to that to get an angle and to find the new length of something is what that is. Have a look at your review. I might have copied an old one off, I'm not sure. What do you got there? You've got, yeah, 0.05 and 0.02 for the original strains there. I think that's what you've got. I hope so. Look at these numbers. Make sure they ought to be 0.05 and 0.02 on that review that I gave you. Is that working? Is that what it is? 0.05 and 0.02? Is that what it says here? It's about almost at the bottom there.
200 U, 500.
Okay, why don't we change that then? So make that, instead of 200 and 500, make it just a decimal, 0.02 and 0.05, okay? And the problem, you're looking at what the problem looks like right there. So it ought to say 0.02 and 0.05. There's some different editions of this floating around. I'm always editing things, but we doing all right with that? We got it? 0.02 and 0.05? Just have a look and make sure, because apparently there's some old ones that don't say that. So just so we all have the same one, let's use that, okay?
Same with that 0.03, we have 300 micro.
Oh, yeah, thank you. Yeah, the 0.03 then, yeah. And it's, they're the same ratios of numbers, but I've kind of increased them is what I've done. So 0.05, 0.03, and 0.02. And for those of you online, just make sure that the online version says this. I'm pretty sure it does, but just check and make sure. Okay? We good? All right, now the last one is an example, and I just want to call this one out. We just got a minute or two here, but this one trouble with testing strengths is the equations take so dang long to run. And so what I've done in the past is I've set up something like this, where I say, okay, here's the situation. Don't actually run all the numbers. Just tell me how you would run the numbers. So what I have here is a table set up where you tell me what equation you'd use, what values you would put in, and what numbers you would get out. Okay, so that's what I'm doing there. So I have that set up. Instead of actually calculating things, you're telling me how you would calculate them. And you might notice that, you probably have noticed that I've numbered the equations on the formula sheet. That's one reason I've done that, so you could do something like this. So the idea here is instead of spending 15 minutes running a bunch of calculations, you just tell me how you would do it. And I want to know what equation you use, but I also want to know what are you going to put into the equation and what number, what will you get out. Okay? So that's the idea on this. We could probably go over some of these problems on Monday if you want. Okay? So we'll go over these on Monday. So we all clear on what I'm getting at there? Okay? So, we'll see you all tomorrow. So tomorrow we'll get into some new stuff, centroids, I think, and moments of inertia.